So, we were developing a dynamical system theory for flow instability using DNS results, and looking at the flow past a circular cylinder, we have shown here the computed lift coefficient variation with time for 3 different Reynolds number 60, 100 and 250. There are certain features that immediately comes to the fore. Number one is that you see that of course, with the increases in Reynolds number, equilibrium amplitude increases. The other thing that you also notice is that there are certain interesting features. For example, this saturation amplitude variation with time is very minimal for higher Reynolds number, but while you look at r equal to 60, although one would expect from Landau's theory that you would have attained an equilibrium amplitude, but it is not so. You can see quite a bit of jagged edges, and it's something specific about this particular lower Reynolds number that is where you see most of this variation. So, we will like to make some comments which we have stated here, that if we increase if we decrease Reynolds number, we see more and more number of modes present. If it was just a single mode, then you would have seen a very nicely developed homogeneous amplitude variation. For example, for r equal to 60, we saw that even in the equilibrium stage, you have significant variation of the amplitude. That implies that there are more than one modes present, isn't it? So, that is what we are saying. Presence of multiple modes are noted with decreasing Reynolds number. For this reason, we will focus our attention to the results at r equal to 60 to see what these multiple modes are doing, and we will also develop what is called as the Landau-Stewart-Eckhaus equation. We kind of resurrected this study year and a half ago to see that unlike what Landau-Stewart equation is, that talks about only a presence of a single dominant mode. Now, if we assume there are more than one modes, then how do we account for it? So, we developed a kind of a variation which was originally proposed in a monograph by Eckhaus, but largely forgotten, but we want to see how we can make use of that. Okay, so, now to make use of that, we are basically talking about the variation of the instability modes with time. That is what your Landau equation is. But we have started discussing about POD, proper orthogonal decomposition. This is the way that we go through. I have just jotted down the steps. Let us say we solve the vorticity transport equation in a time horizon spanned between t 1 and t 2. Then we can split the instantaneous value of the vorticity into 2 parts, a mean or an equilibrium part plus a variation. The mean part is defined as some kind of a time average. So, this is the time interval over which the data has been obtained, and we take this and obtain this omega mean. Having obtained the omega mean, it is straightforward to obtain the disturbance quantity, which is nothing but the instantaneous realization minus this mean. So, let us now briefly talk about what that method of snapshot is, which was developed by Syrovich. What we do is the disturbance vorticity that we have obtained here represented in a Galerkin ansatz. So, what is it? It is some kind of a splitting the variable variation with respect to space and time into a time dependent amplitude times a space dependent function, right. So, what we are doing? We are representing the total disturbance quantity in terms of let us say m such snapshots. So, we take pictures. we have the simulation, either you have done it through experiment, better be you do it with numerics, because there you will have more control. Then what you do is you try to construct what is called as a covariance matrix of this disturbance field. So, that element of that covariance matrix is called here as Rij. So, that is obtained by taking the snapshot of the disturbance field at time t I and the snapshot taken at time t j. So, what we are going to do is basically we are taking a product of the two functions at these two times, integrate over the whole domain, right. Your x vector indicates your the domain. What I am showing you here is in terms of a 2D simulation. That is why we are talking about the elementary volume or elementary area as d2x, but you could extend the same idea for 3-dimensional flow field as well, right. Well, you could trivially also do it for 1D. Now, what happens is this Rij is obtained by application of Hilbert-Schmidt theory in calculus of variation, which we are not going to do, but which states the following, that if I have this on sorts of time dependent amplitude times this, that space dependent function actually works out as an eigenfunction of this equation. Okay. So, this is that covariance matrix, this is the eigenfunction phi m, lambda denotes your eigenvalue. Okay. This is a fairly well developed theory. So, what we are going to do is we have obtained the disturbance field, from there we will construct this. Once we have this, finding out the eigenvalue of a matrix is very easy. These days you do not even have to probably write your own, there are many readily available tools available to calculate the eigenvalues and eigenfunctions, right. So, that is what you would be doing. So, solving this equation, you will simultaneously be obtaining lambda as well as phi m, the eigenfunctions. What does this eigenvalues give us? These eigenvalues tells us the probability of the occurrence of those eigenfunctions. Okay. And if I sum up all this eigenvalues, then that will be the providing the total quantity that is under investigation. What is the total quantity under investigation? So, this is basically a square of vorticity here, that is what we call as the entropy. So, entropy field will be obtained in terms of the product of this functions. Okay. So, lambda is a very good measure of the entropy content of the disturbance field. Okay. So, this is how we are going to live with performing the analysis, POD analysis, by focusing our attention on the flow for r equal to 60, and I explained to you what is our main incentive. We are trying to establish why we get multiple Hopf bifurcation. Multiple Hopf bifurcation due to what? Is it due to say qualitatively different instabilities at different Reynolds number, and when these instabilities occur, they are still dominated by this corresponding single mode, or what we saw in terms of the time history of the lift, and what we saw for r equal to 60, there was presence of multiple modes. So, maybe all these multiple modes are present and they selectively dominate in different ranges of Reynolds number, and 60 Reynolds number case was very specific, where we saw a visual signature of such multimodal presence. So, that is what we are going to do. That by and large, if you look at instead at the highest Reynolds number that we have shown at 250, we get predominantly single frequency, while in case of 60 r equal to 60, we have multiple frequencies present. So, that is what we are talking about here. You can see if it was dominated by a single mode, we would have had a nice envelope, not a jaggedy envelope that we are seeing here. Okay. So, That being the motivation for focusing our attention for the results of r equal to 60, we will go ahead and we will see what we can do about it. Even when we take the results for this r equal to 60, what we are going to do is basically study the same data, but over different time ranges. So, T1, T2 I will purposely choose over different time ranges. Why we want to do it? Because you see, study of POD as a tool has been gone off on a particular route to exploit its I would say engineering usage. For example, like let us say you are listening to a piece of music and it occupies some amount of memory. Now, what I could do is I could take that signal and I can do a kind of a modal decomposition. And if I have, let us say, 1000 modes and I see that most of the signal noise is contained within first 10 modes, then I can do this modal decomposition and only store 10 modes. And what happens? Instead of, let us say, 10 megabyte, I can get the same quality of signal. It is only with very good acoustics or very discerning ears, people can distinguish between the 10 modes and 1000 modes, right. But by and large, in a commercial scenario, those 10 modes will do well. And this is what people have been doing in one of the applications, data compression, right, massive saving. Similarly, people have been also using POD as a tool to control flows. If I understand that these 10 modes are most important, then I should be able to control those 10 modes instead of worrying about 1000 modes. I can develop strategies to control this. So, what has happened is people have been talking about mostly from these aspects, exploiting their engineering usage. Thereby, people are not too particularly interested about seeing what happens during the transients, like especially in the context of fluid mechanics. You have initially a very large transient and then the flow settles down to some kind of a statistical stationarity. So, if you are interested in looking at only the statistically stationary position of the signal, there may not be much of a motivation or incentive to look at the transients. However, as I explained to you that our point of view is totally to decipher the physics of the phenomena of instability. So, we want to study how we get to that statistical stationary state. That information may be embedded to the system what happens during the transient. For that reason, what we will be talking about, we will take the same time series and we will look at 3 different time intervals and to find out what is happening. And the results would convince us that we would be having quite a bit of a success. So, let us basically focus our attention to this flow past a cylinder at Reynolds number of 60. We have actually done a simulation from let us say 0 to 430. That I will call it as case C. So, that is the full trace, time trace. What we can look at? We can look at a subset of it 350 to 430, where you may have arrived at as that statistically stationary path. So, that is your case B. So, by 350 all the transients would have gone. But then we can also take a case which I call it as case A, which will have some bit of late stages of transients plus the equilibrium state. So, let us look at this kind of things, and then we can perform this analysis, obtain these lambdas, and this table actually shows you the lambdas for these 3 different time ranges. When I look at the full time series, then I see the eigenvalues given by this. Okay. These are raw eigenvalues. Okay. Now, you may notice that there are some missing spots. I will explain why it is so. Historically, the early practitioners of POD in this particular field, especially about flow past blob bodies, what they noticed? They noticed that you get this eigenfunctions, they kind of occur in pair, and this pair formation is quite significant. However, sometimes in the early part of this decade, Nowak and his group from Germany, they discovered that talking about this modal behavior in terms of these pairs is not adequate. There is something that sticks out, which they called as the shift mode. So, what it means is that if I look at the behavior of the dynamical system without the shift mode, they will be just about varying about a 0 mean. But when you look at the experimental data, you will be seeing as if there is a kind of a mean shift. So, there has been a shift in the mean flow field. To explain that, they modeled what is called as this shift mode. However, in contrast to that effort of Nowak, what we are doing here, we are not doing any kind of modeling. We are taking our full DNS data and then just performing the POD analysis as it has been proposed here. And what we noticed that whenever we have these shift modes, they do not occur in pair, they occur individually. So, what I find here, this third mode is one such isolated mode, which does not form a pair. That is why we leave a blank here. Then of course, we have another pair followed by a single mode, another single mode here, and so on and so forth. And you also notice that when you have the pair formation, the eigenvalues kind of have a similar magnitude. So, looking at this data set itself, you will make out which is forming pair with what. Like the first is forming pair with the second, this one is forming pair with this, and so on and so forth, while this last two, 13th and 14th, also form a pair. Okay. Now, this is for the full time series. Suppose I look at only the equilibrium state, look at the data set from 350 to 430. Then what we notice, it is only a story of 3 pairs, nothing else. And you can ask me that why did I put all those blanks here? That is because of the essential nature, because this is the most predominant one. So, that better come there, and you also know that there is this hierarchy of these eigenvalues. Higher up the position of eigenvalue, more energy it contains, because what we could do is we could look at a cumulative entropy distribution that basically gives you, which I may call by let us say number epsilon j, which would be written as some lambda j divided by summation of all lambda k going from 1 to. You understand why it is m, because we have taken m snapshots. This is a m dimensional matrix, so I will have m eigenvalues. Okay? That is what we are going to do. So, when we look at the equilibrium state, we only have 3 pairs. When we look at this particular case A, which is a admixture of a late transient and the equilibrium state, we of course obtain a pair here. We also obtain a shift mode, and then we have another pair here and the pair there. Okay. Now, what we need to look at here is how we get this POD performed. That when I look at case C, I am also including the impulsive start of the flow. At time t equal to 0, the flow was considered inviscid. That was our initial condition, and then we saw how the flow picked up its viscous action. So, that is what we are doing here. How do we perform this POD? How densely we take the data? What we notice here, that here we have taken 5 snapshots taken in unit time interval. So, if I am talking about 0 to 430, I have taken a snapshots of 430 into 5, right. So, you can see it is more than 2000 snapshots I have taken. This is significantly different than what people have been doing before. Even we did some of those POD studies for bypass transition, as I showed you earlier, when we are looking at vortex induced instability by aperiodic vortices. What we did there, of course, we took only about 10 snapshots or 20 snapshots in an interval of 10. But here we are talking about taking 5 snapshots in unit time interval. This is important. This is important because irrespective of the accuracy with which you are doing your direct numerical simulation, the sampling rate of the snapshots will tell you what is the frequency range you are able to display with the POD. If you take too few, then you know within the Nyquist limit you will be getting only very few peaks. So, that is why sometimes even in recent times, I think we are even doing PODs where we are taking what, about 40 snapshots in unit time interval, 40. So, you can see, and please do understand that taking insufficient sampling rate will always mislead you into drawing wrong conclusion. So, it is better that you go on the side of caution and have more data than less. Okay? So, this is something that we need to understand. Now, we have already stated some of these things, that for example, the case B encompasses the range from 200 to 430, which partly includes the late transient and as well as the saturation stage of the flow evolution, while this particular time interval 350 to 430, that is the case A, it only contains the equilibrium stage. And the total entropy content during the equilibrium stage requires very fewer modes, okay, for its correct description as compared to any case that included the transient stage. In all these things that I have shown you, here most of the time we have accounted for the total entropy content in those retained modes to that level of about 95%. Okay. So, what happens is for the case A, those 6 modes accounted for 95%. That is why we did not go any further. Okay. Now, if I look at all the cases, that is what we are saying, that if we take go about up to first 14, 15 modes, then we account for most of the entropy, and of course, higher modes keep on contributing incrementally smaller and smaller quantum. So, that is what we need to understand. This convention of identifying modes pairwise was used by this group, Dean, Karniadakis, and Noack et al. This is the work that I was talking to you about. Noack's work is one of the most interesting and outstanding work in the last 1 decade. And well, all of them thought you need to worry only about the primary modes. If there are non-pair forming modes, Noack only talked about one such mode. Okay, it's one such mode, and but you saw the table that we projected when we took the data from 0 to 430. We had many isolated modes. In fact, in that 14, we had about four such modes. So we do not call them these modes as shift modes. We have classified the POD modes into the following group. One is, of course, what we will call as the regular modes. Well, regular in the sense what everybody thought originally would be. They are basically caused by pairs. Then we talk about those modes which do not form pairs. This we call anomalous modes. And here in anomalous modes also we subdivide into two groups. Anomalous modes of the first kind, which we will call as T1 mode. This we call as the R mode. And we are going to talk about a third classification, which is also anomalous modes, but they do form pair. So this T2 mode that we are talking about, they also form pair. Why we are calling these as anomalous mode is simply for the reason that their time variation, when we relate these POD modes to the corresponding instability modes, they will not follow Stewart-Landau equation. That is why we are calling anomalous. Whereas regular modes, we can show, as we have seen from the CL plot, that it starts off with a linear instability and saturates. That is your Stewart-Landau equation. So these regular modes follow that kind of variation, whereas T1 and T2 modes will not do that. And what is the difference between T1 mode and the shift mode? Noack predicted only one single T1 mode, and he assumed that mode is present at all time. Now we are going to see results that this anomalous mode of the first kind, they appear singly all right, but number one, they do not appear as one. There are more than one modes, like what we would see in case C when we take the data from 0 to 430. And then secondly, we can also see that they do not necessarily remain invariant with time. This anomalous mode of the first kind, they are a strict function of time. So if I look at the flow past a cylinder, this is what is always observed. Modes 1 and 2 will form a pair, and the modes will be roughly 90-degree phase apart. Now, this might raise a query from your side, why it is roughly 90-degree and not exactly 90-degree. While we are talking about orthogonal decomposition, so what does that orthogonality mean? Orthogonality would imply strict 90 degrees. But you recall also what Kosambi started off with his motivation, that you have a stochastical dynamical system. You are projecting it into a deterministic basis which are orthogonal. So if I look at some of those modes which form pair, and the phase difference is not perfectly 90-degree, that shows that even these pairs are contaminated by stochasticity, right? So that is the main issue. We need to understand that. This work done by Dean and co-authors, they propose that what you see as the vortex shading is due to the interaction between the leading pair of eigenmodes. That's what it is, right? A1 phi 1 and A2 phi 2. And then they said the way they interact, that defines the travelling nature of those shed vortices. And this is what I've been telling you, that Noack et al. Were the first to deviate from the earlier work on POD by stating that the dynamics of the wake is determined by the presence of a mode, shift mode, which is a solitary mode, does not form pair. So this is what we said already, that if I look at the POD modes and they appear in pair, then we will call them as regular modes when they follow Stewart-Landau equation. If they occur in pair and do not follow Stewart-Landau equation, then I will not call them as regular modes. I will call them as the T2 modes, right. So this is the taxonomy. So this is your definition of anomalous modes. Modes appearing alone or do not follow the time variation given by Landau equation, call them as anomalous modes. So whenever I will have an anomalous mode which appears alone, the next line I will put a dot. That's what I did when I plotted in the table. Whenever I saw a single mode, I left a dot blank. And then I did the counting. So when I say there are 14 modes, that does not mean all the 14 elements are filled up. There would be, say, 1, 2 present, then 3 is there, 4 is missing. Then I could again have the 5th mode, 6th missing, and so on and so forth. Okay. Now, if I calculate this lambdas and plot them, what am I doing? I am actually summing up this epsilon j's slowly. So for the 3 data set, I am showing you the result. The red curve corresponds to the full data set from 0 to 430. So the first mode contains about 30% of the total. Okay. The next one also contains about 30%. So this two together accounts for 60% of the total entropy. The third mode takes you there up to about, let's say, 84, 85%, and then slowly it goes up. And if I want to look at this is almost, say, 99%. This, when I take the full data set, it approaches there requiring more and more number of modes. Whereas if you look at the pure equilibrium state, where we have taken from 350 to 430, then you see we reached that 99% within the first 6 modes only. Okay. And you also noticed that what we obtained there, we just simply have one pair, 1, 2, then we have another pair, 5, 6, and the last mode was 13, 14, because we said, look, whatever the last one accounts for the 99%, that will be in the first 14 modes. So that's what we are going to get. Whereas the intermediate data set between 200 and 430, we see that's the way it is. So you see, you have now a very powerful tool to explain how the disturbance vorticity field is in terms of this lambda, and what we can do is, having obtained the lambda, I can solve this equation and obtain these eigenfunctions. And what these eigenfunctions are? These eigenfunctions are functions of both space dimensions. So I am going to get a spatial portrait, and this is what we are showing you the data, the 5 functions for the case of 0 to 430 when we have taken the full data set. Okay. What you notice is mode 1 and mode 2 looks like this. And now you have no reason to suspect why we paired them together. They look almost same. Okay. Okay. So now you see that why I said that to draw a composite picture looking at one sub-component is not good enough. Lambda gave us some information. Eigenfunctions gives us something more. That's very, very interesting. Now we can see why we paired them together. This looks like a complement. And you can very clearly see the complementary nature. These are essentially what? Vorticity information as a function of space. The positive vorticity is shown by the solid line. The negative ones are shown by the dotted line. Okay. And you can see a kind of a shift of one with respect to other by 90 degrees. That's why where you see in this case as positive, there you will see negative. So this is a complementary picture. That's what you are doing. And you see this was the so-called the T1 mode or the shift mode, the first shift mode. That's what we get. And this shift mode is qualitatively different than what you see as the regular modes. That's why we would call it anomalous modes. They are not the same as we see here or here. And this is again a pair. This is again a pair, and you can also see the maximum minimum ranges are given. They are almost similar when we look at the pairs, and there is a kind of a similarity in the vertical structures too. This is fifth, and there is a sixth mode. Fourth mode is missing. Now we have the next isolated mode. We are calling it as a seventh mode. So eighth would be missing, right? So this is the way that we are going to see. And you also understand the way we plotted those, that as the mode number kept increasing, the relative contribution kept on shrinking. So don't be too much enamored by a interesting looking structure, because that may actually contribute to very little. But at the same time, we must understand that we are doing an instability study. So one of the cornerstone of instability study is small cause having large effect. So that's why we keep showing as much of the energy content modes as possible and entropy content modes as possible, because some of them may decide upon what is going to happen. And you see, this is the spatial variations, right? So the next mode is also an isolated mode, ninth mode. So 10 is missing. Then we have another isolated mode which we'll call as mode 11. So 12 is missing. Then we have the finally the pair 13 and 14. So you have now a fairly decent idea how we went about forming this composite picture. So we'll look at it as we go along. So we are not too interested about this only the space variation. We would like to also get into the time variation. That's important. And what is the time variation? Time variation is given by this. Okay. So what we say, this is our eigenfunctions, POD eigenfunctions. And this is what we will call it as POD amplitude functions. Now, what we just now seen, we have seen how lambdas vary, how phi j's vary, but we still haven't talked about the time variation. So, we need to do that. To do that, we need to find out what this POD amplitude function is going to be. We have talked about all of this. We just want to point out one thing about the case C, that phi 1, phi 2, phi 5, phi 6 represents regular modes showing alternating vertical structures in the wake. And what we notice though, this 13 and 14 forms a pair, but their time variation is not like what we are used to seeing. What we are used to seeing is that sketch that we have shown before. That Stewart-Landau equation would show is kind of a time variation which will pick up from this and then will reach this equilibrium state. So, that is your Stewart-Landau mode. This 13 and 14, if I look at the time variation, then they will not show this kind of linear instability followed by nonlinear saturation. This is somewhat different. How do we know this time variation is? Well, that should come from this. So, we have to get this. Now, if we call these functions as orthogonal functions, then what I could do? I could obtain this AJs or AM of t. How do we do that? How do we do that? They are orthogonal. So, if I have this, I multiply this by phi m and integrate, then what would I get? So, if I take this description, and multiply this, let us say, by phi j, and then integrate over the whole domain, what would I get from this side? Only I will get AJ times so I can get AJ. That's it, right? So this is the whole concept. So we can do that. So basically, if I want to summarize case C, which we have seen so far in terms of the leading eigenfunctions, mode 1 and 2 along with mode 5 and 6 form regular pair. Modes 3 and 7 are anomalous modes of the first kind that appear without forming pair. Modes 9 and 11 are also anomalous modes of the first kind. Mode 13 and 14 are somewhat different, and that difference is obtained by noticing this. I will show you what they would look like. These are those AJs that we have, that we can obtain from here. So this is your A1 and A2 plotted together, and you see they form such a nice pair. They complement each other, time shifted. Okay, that's what you see. This is your A3, and A3 is got a very, very interesting behavior. Initially, of course, after impulsive start, it has a large value, then it goes to the other side, becomes negative, then it remains flat, and then once the linear instability starts, then again it picks up and it settles over there. Okay? And although you see, recall what Noack said, that this is going to be present at all time, which is not true. You are seeing there. It is present at all time later in the equilibrium state, but also this is not steady. You are seeing this fluctuation, and this fluctuation is something like a Strual frequency. This is characteristics of that. So you will get that. Now A5 and A6 form this mode, that we can very clearly see. Then A7 was a anomalous mode of the first kind, and once again we are seeing the same thing. See, what happens is when the linear instability is not there, they are kind of flat, time independent, but some non-zero values. So this value being non-zero and shifted up, really prompted Noack et al. To call it as a shift mode, as if it has shifted the whole thing by a datum. Same thing about A7 that you are seeing here. Let us go through and see the other modes, and then we will find out what we are talking about. The next two were, we said, are going to be anomalous mode of the first kind. That is your 9th mode and the 11th mode. This is also something similar that you are seeing. And as you can see that as you go to higher and higher mode, their contributions are coming close to 0. Right? So when I represent this contribution level should come from the magnitude of m. What lambda gives here is nowhere present here. So we make that observation that lambda determines the relative contribution. But what we are noticing here, when I represent the disturbance function, the relative quantity contribution would come from m, and that is what you are seeing. They are very, very close to 0. As you go higher and higher, their contributions are smaller and smaller. This is the interesting bit. I told you that the 13th and 14th form pair, but they do not go like some kind of saturation. They appear like wave packets. They are like wave packets. So they are present in some time, then quenches there, then again it picks up. And if we would have done the calculation, again it would have come down and gone up, and so on and so forth. So this is what we call as the T2 modes. So now you understand why we are calling this. In fact, in recent times we have been looking at airfoil aerodynamics. Yogesh is looking at that with great care, and we are seeing some different instability mechanisms have different footprints. But by and large, this general classification is nearly universal. This is nearly universal. I will not be able to show it to you. I will give you the reference in the next class. But we have seen that same type of properties. Okay. Now, this is another picture what we have done for case A. What was the case A? Case A was for 200 to 430, right? So what you are seeing here, again the leading eigenfunctions forming pair. This is your shift mode, and 5th and 6th again is a regular pair, and then there is nothing in there. You go all the way up to 13th and 14th, which is the T2 mode that we just now saw similar behavior. So this is what we are going to see. So you understand that there is a need to really further explain why and how these things relate. This is your case B, where we have just looked at the data set from 350 to 430. And you can very clearly see 3 pairs. That is it. And that takes care of everything. So, you know, if you are trying to exploit POD analysis in terms of flow control, etc., and if you are only interested in the steady state, then probably taking a small such data set once you have reached the equilibrium stage is quite good. And then you will have to only worry about this very few modes, and you should be able to control them to your advantage. But when it comes to understanding flow instabilities, it is always better that you take the full data set, because you want to explain how you have arrived here. How you have arrived here. In the next class, I will explain to you what is the source of these anomalous modes. Why do they appear? That is rather important. And this we have seen. So let's make some observations when we are looking at flow past the cylinder. We can easily understand the trend of the time variation of the paired modes at early time as the disturbance grows from 0. It is not so for the anomalous modes of the first kind, for which the amplitude functions vary very rapidly during the transient state. This is rather important. So basically, the shift that you are getting in the final state, the history lies there. So that's why it is necessary for you to take the full set. Otherwise, you will not be able to say why you have arrived at that particular equilibrium state. That shift has occurred in a transient manner. Okay? And to generate POD amplitude functions from the Navier-Stokes equation is not so easy. What we have done here, we have obtained the solution, we calculated the disturbance vorticity, and then we calculated A of j. What some people have done, they have tried to put this back into the Navier-Stokes equation and try to derive an evolution equation for ages. So what will happen? Of course, you have all these modes. So the basic intention is to convert the PDEs into ODEs, because your space dependence is given in terms of your phi's. So once you have put in that information and integrated over the whole domain, then you will get that. But there is a problem. If I am looking at, let's say, the Navier-Stokes equation in UV formulation, then I may have this kind of depiction for the velocities. What about the pressure? So that's where some people have done some kind of a cardinal sin. They have actually omitted the pressure term. And that is one problem. And there is another problem that we'll be talking about when we meet the next time. Okay?